Good afternoon, Warrington. A pleasure to be back, and yes, to give you parts 4 and then part 5 of the series on exploring the solar system. So this one, part 4, is on exoplanets, planets around other stars. So we can ask the question, why bother looking for exoplanets? How do we go about finding them if we are interested in finding them? And how we go about looking for life, given that life might well be out there. And I'll ask the question at the end, what next in terms of what missions are coming up that might impact on our knowledge of exoplanets. So one of the reasons for looking for exoplanets is to try and address the question, do we believe our solar system is typical? We've been studying our own solar system for quite a while. We know about the planets, the minor planets, the comets, the asteroids, etc. But would we expect the structure or the composition of our solar system to be reflected in other solar systems that are out there? Are there any other solar systems that have planets like the Earth, for instance? And if there are other planets like the Earth, what are the chances that there is life elsewhere in the galaxy? And even if there isn't life out there, then we think that studying other solar systems will probably give us better understanding of our own solar system. So how do we go about finding exoplanets? There are at least, probably more, but there are at least 5 different methods that can be applied for finding planets around other stars. You appreciate the problem, planets are small and dim, and stars tend to be a lot bigger and a lot brighter. So it's rather tricky simply to look out there and look at stars and say, are there any planets buzzing around those stars? It's a much more technically difficult problem to address. I'll be talking about 3 of the methods because those are the methods that produce most of the exoplanets that we understand and have catalogued to date. I'll be mentioning 2 others, but those are in the handout. I won't be covering those at any great length. So the 5 methods. The first one is looking at radial velocity, the velocity along our line of sight to a star. Even if we can't see the planet can make the star wobble because as the planet goes around the star, strictly speaking, the planet and star go around about their common center of gravity, or center of mass, and therefore the star wobbles if it's got a planet going around it. And therefore, if the star is moving sometimes towards or away from us, we can see that in the spectrum of the star. A second method involves a planet that might happen to move in front of the disk of a star. Doesn't happen that often, won't happen if we're looking down, as it were, from above a solar system. But if we're looking at a solar system edge on, a planet might move in front of the disk of the star and reduce some of the starlight temporarily. So we're looking for shadows in the amount of light coming from a star. Third method is direct imaging. Stars being much brighter than planets by possibly 1,000,000-fold, that's part of a problem. But if we can block out the light from a star, and that can be done with a so-called occulting disk, a very small disk placed inside the telescope, it can block the light from the star and hopefully allow us to see any much fainter planets that might be buzzing around it. 2 other methods which I'm not going to talk about in any length because they haven't found many exoplanets, but it is also possible to find exoplanets using gravitational lensing, in other words, the bending of light as the light passes through a solar system, and it's also possible to see the evidence for exoplanets by looking at whether or not stars in the night sky actually appear to move, if you have enough precision with which to measure those stars. So let's have a look at those methods and see what they tell us. Radial velocity. So here we're looking at it from above, but if we look at it more from the side, we can see that as a planet moves and the star moves around the common center of gravity, sometimes the star is moving towards us, sometimes away from us. Now this particular cartoon would imply that at the bottom the star becomes a little bit redder or a little bit bluer. It's not quite like that, but yes, if we look at the spectrum of the light from the star, so again, as seen from above, they're moving around the common center of gravity. As seen from the side, the star seems to go a little bit back in front. But what's important is the speed, the radial speed, the speed towards us or the speed away from us. Because as the star moves towards us or away from us, we don't necessarily see the star look blue or look red, but if we look at any features in the spectrum by taking the light from the star, putting it through a prism or a diffraction grating, then we can see any features in the spectrum move towards the red or move towards the blue, depending on whether the star is moving away from us or moving towards us. So if there's a planet orbiting, we'll see these lines go backwards and forwards, with a period that corresponds to the orbit of the exoplanet. The transit method, method number 2, relies on the fact that we're looking at things edge on. The previous method relies on the mass of the planet making the star wobble. Here, we're relying on the physical size, i.e. the diameter of the planet, literally just blocking light from the star and causing a dip in the amount of starlight that we see. Again, we don't have to be able to resolve the planet. We simply look at the amount of starlight we're getting from a particular system, and if we see a characteristic dip that looks like that, we can deduce that a planet has moved in front of the star. A large planet basically blocks more of the light from the star, and so a large planet will give a much deeper dip compared to a small planet which only blocks a smaller fraction of the light. So the depth of the dip, are we losing 0.5% of the light from the star, or 1%, or 1.5%? Generally speaking, planets are quite small compared to stars, so we can't expect it to be a big dip, but if we measure how much that dip is, just literally quantify how much has it fallen compared to the original light from the star, we can get an estimate of the diameter of the planet. Not only that, but it works reasonably well if we have multiple planets. So here we have a hypothetical system comprising 3 planets. As a large planet goes in front of the star, we get a dip in the amount of starlight, and then that moves off the disk and the starlight returns to normal. But now we have a second planet come in and then a third planet. And so the pattern of light that we see, the drop and then the rise, it's more complicated, but we can effectively deconvolve, work out what planets must be there in order to give us that particular arrangement, that particular change in the light output of a particular star system. So it involves measuring the light from a star. We would like it to look like that as a function of time. What we actually do is take measurements of the star brightness, and we get a lot of data points. Once we have a lot of data points, we then fit it and say, what is the best shape that explains all of the data points that we've got? The more data points we have, the more precisely we can map out the change of brightness, and then the more information we get about the planet. This is a real set of data taken from the James Webb Space Telescope. You probably can't read the scale, but here the sunlight is defined as 100%, and then it drops to about 98.5%. So in this particular case, the planet has only blocked about 1.5% of the starlight, but with enough data points, we can get a very clear dip, which tells us about the size of the planet and something about the nature of the planet, which I'll come back to shortly. The third technique, direct imaging, involves taking an occulting disk and blocking out the very bright starlight, which hopefully will then allow us to see a much fainter object that was there. This is just a snapshot. Remember, stars are very bright, so if we just take an instantaneous image of a star, we get something that might look a little bit like that. But the point is that faint planets might be there, but almost impossible to image when we've got something 1,000,000 times brighter sitting right next to them. So if we can somehow block the starlight, then we have a chance of seeing those fainter planets. And this has been done for a few systems. There's an occulting disk right in the middle, blocking out the starlight, allowing us then to see individual planets moving around the star. This is a time lapse taken over quite a long time. Over 12 years, we see the individual motion. If I run that particular animation again, you see the planet closer to the star is moving quite quickly. The planets further away from the star are moving more slowly. Just like Mercury goes around the sun quite quickly compared to Venus, Earth, Mars, etc. So that was a time lapse. You have to be quite patient because, of course, if you're trying to see the motion of planets, which might take years to go around their host stars, then you can't just take a snapshot and see a planetary system and deduce what's there. How do you know that's a planet rather than a more distant star? Only by taking data over many months or many years can you be convinced that you are actually looking at a planetary system. It works even if the planetary system is edge on. Here an occulting disk blocks the star, but the planet is visible on one side of the star and then invisible and then visible on the other side of the star. So again, as long as the planet is far enough from the star that we can block the starlight and still see planets on one side or the other, again, this was a time lapse taken over many years, and then we can be convinced that we can A, see a planet which is definitely going around the star, and we can get an idea of the timing, i.e. the period, how long it takes the planet to go around that host star. James Webb, again, has taken images of various star systems that are thought to be nascent stellar systems with planetary systems around them. In other words, again, we take a bright star, we think there's evidence that a planetary system is forming. We block the light from the star. So there's an occulting disk blocking out the very bright starlight. James Webb has the advantage that it works in the infrared, which is very good for finding relatively cool stuff. Optical frequencies, optical wavelengths are very good for looking at stars because they emit a lot of their light in the ultraviolet and the visible part of the spectrum. But dusty regions around a star indicating a planetary system in the process of formation tend to be a lot cooler, and they emit more strongly in infrared than they do in visible light, so the James Webb is well suited for looking at the dusty environments around stars in the process of forming planets. In this particular case, it looks like there were no planets actually there. It was thought that maybe there was a hint of something coalescing into a planet, but it turns out that's not to be the case. It looks like it was just a little concentration of dust rather than a planet being formed. But it does seem like this dusty region around this star seems to have structure. It's almost like we were looking at a very early version of, for instance, are we looking at a planetary system in which there's something akin to an asteroid belt or something akin to a Kuiper belt sitting out there, a lot of icy particles beyond the orbit of Neptune. So we can't see individual planets orbiting, but we can get the hint that planets are in the process of formation. And the more systems we look at, the more we think planetary systems are not necessarily ubiquitous, but they are very common. A few decades ago, we really weren't sure whether many stars had planetary systems or whether it was a unique feature of our sun and our solar system. Now it looks like planetary systems are almost everywhere. If we're lucky, we can apply more than one technique for looking at a particular planetary system. Remember the wobble technique, the idea that massive planets will make their stars wobble. That can be determined spectroscopically, and it's relatively straightforward to get data from that method. With transits, we rely on the fact that the orbital plane is such that we see planets going in front of the star, so that's less likely. But every once in a while, we do find that we can get information from both techniques on the same planetary system. So if we can apply the radial velocity, the wobble technique, the spectroscopic technique for getting the small changes in radial velocity of the star, as well as looking at transits, then we can get information. Remember, radial velocity depends on how massive the planet is, making the star wobble, whereas with transits, the amount of light that's blocked depends on the diameter of the star, of the planet. So we can get mass from one technique, and we can get the size from another technique. If we're using spectroscopy to get the radial velocity, we can also use spectroscopy to get information about the atmosphere, which I'll come back to in a moment. But the point is, if we have mass and we have size, then using those two quantities together, then we have an estimate of the density of the planet. If the density is quite high, then we're probably dealing with a rocky planet. If the density is quite low, we might be dealing with a gas planet. But with mass and size, we can get an idea of what sort of planet we are talking about. And if we can identify the host star, is it a very hot star, a big blue supergiant? Is it a very dim star like a red dwarf? If we get an idea of the mass and the size of the star around which this planet is orbiting, knowing the period, we can work out how far away it is, or with direct imaging, we can see how far away it is from the host star. We can get an idea of what the temperature of the planet might be. We can't necessarily take into account the atmosphere. In other words, the Earth is quite warm because we've got an insulating blanket around us compared to, for instance, Mars, which is not that much further away from the sun, but is a lot colder simply because Mars doesn't have a thick atmosphere to keep it warm. But if we just think about the equilibrium temperature, the temperature that something would come to if it was placed at that distance from its host star, then we can get an idea of the temperature of the planet. And then we can tell if it was, for instance, something with about the density of water, we might be able to tell, is it likely to be an ocean planet or is it likely to be an ice planet? If it's a rocky planet but very close to its host star, is it more likely to be a lava world, for instance? With all of these little bits of information, they all contribute to the jigsaw and build up a picture of what that exoplanet might look like. And that has allowed us to build up the exoplanet zoo. This is not all of the exoplanets we know about. This is an infographic that shows a small fraction of all the exoplanets that we know about, positioned here according to what we think their equilibrium temperature is on the horizontal scale, and they're all shown to scale in terms of their size. This shows, I don't know, about 1,000 planets, but the total number that we found so far is about 6,000. So this is only perhaps 1 in 6 of all the planets that we know about. So as I say, they're on a horizontal scale, where very cold planets are over on the left, minus 200 Celsius, and rather hot planets are on the right-hand side. I've indicated roughly where plus 200 Celsius is. And just for scale, I'm sure you can't pick them out easily, but just for scale, in the bottom left-hand corner there are some of our familiar planets. Technically, they're not exoplanets, but just to give a sense of scale, back down in the corner there, we've got Jupiter, Saturn, Uranus, and Neptune. And so you get an idea of the size of other planets compared to the size of our planets in our solar system. If we were interested in, okay, some of them are hot and some of them are cold, but if we were interested in, let's think about which of those planets might be at the right positions around their host stars, such that it's a possibility of liquid water existing. Now, liquid water, it is thought to be very beneficial for the evolution of life, not necessarily absolutely required, but certainly if we have a planet in which liquid water exists, as well as ice, as well as water vapor, it seems like life is much more likely to get a hold. So we can ask, on that scale, over what range would we expect the temperature to be such that liquid water exists? And unfortunately, it's only a few % of all the planets that we've seen where liquid water might exist. We'd have to rule out all of the very cold planets and all of the very hot planets. Anything on the left would be so cold they would just be ice. Anything on the right would be so hot they would just be water vapor, if water existed. If we want liquid water, we're restricted to that narrow stripe in the middle there. Only a few % of all planets that exist might have liquid in which life would exist. Doesn't rule out life in non-liquid water environments, but a lot of people are concentrating in this particular region. And again, for context, let me just remind you, Mars is too far out for liquid water to exist. It's too cold. Venus is far too hot, with a surface temperature of many hundreds of degrees. And this is why it's called the Goldilocks zone, because Earth is sitting in the region where it's not too hot, not too cold, just where ice and water vapor can all coexist, and that's why we have a planet that is so rich in life. So we can ask ourselves, is there anything interesting about any of these candidates we found so far? All of these have been documented and catalogued, and so we know masses and we know sizes and we know distance from their host star, etc. One thing I found quite interesting was, given that we didn't know if exoplanets even existed as of a few decades ago, it's interesting to see that when we look at our nearest star, Alpha Centauri, it looks like, well, life exists there. Proxima, which is one of the stars in the Alpha Centauri system, it would appear has exoplanets. What are the chances that if exoplanets are not very common, what are the chances that we just happen to have a neighbor that also has planets going around it? Statistically, that would seem very unlikely. So although we haven't mapped all of the billions of stars in the Milky Way, it looks like there's a very high chance that a lot of them, maybe not all of them, but a lot of them have exoplanet systems. One of the oldest we found so far, which has gone under the nickname of Methuselah, there's a planet that appears to be 12.7 billion years old. We know of no mechanism whereby a star can be made and then many billions of years later, it can then produce planets. In other words, as far as we know, planets are always born at the same time as the star. So if the star is 12.7 billion years old, then the planet is as well. And this one, when you remember that the universe is 13.8 billion years old, you can see that this planet came into being very early on in the universe. So in other words, we have some understanding of how the universe was born, how galaxies evolve, how stars evolve. It looks like planets came along almost immediately. Planets came along almost as soon as the universe was ready to produce the raw materials to make planets. So making planets doesn't appear to be that difficult. If it was that difficult, it might have taken billions of years before the first ones came along. In the top right-hand corner here, we have a very hot planet because it's relatively close to its star, a surface temperature that's been estimated at something like 4,000 Kelvin. That's a fairly ridiculous sort of temperature to think about. It's not the sort of thing that's conducive to life as far as we understand it. And this one in the bottom right-hand corner that looks a little bit egg-shaped, you think, is that a little bit of distortion in the infographic? No, that's what we think that planet actually looks like. That one is close enough to its host star, only a few million kilometers away, that it's probably egg-shaped because of the tides that are raised on the planet by the star. When you remember that we on Earth are 150 million kilometers away from the sun, this is again right next door to its host star and so has rather extreme tidal effects, pulling and distorting the planet as well as heating the planet up to rather high temperatures. One of the largest that we can see in this particular infographic is that one that goes under the wonderful name of HAT P67b. Astronomers really have to get their act together and start naming these things a little better. But this one is about 10 times the size of Jupiter, and yet it appears to have a mass less than that of Jupiter. We can get its size from transits, we can get its mass from the wobble of the star, but this appears to be bigger than Jupiter, but less massive than Jupiter, which means it must be a very low-density planet. It's been estimated that this has the density of perhaps marshmallow, something like that. So quite what it's made of, we're not too sure, but it appears to be a very low-density object. In terms of the astrophysicists coming up with much better names, that's probably one of the worst ones, HAT P67b. But I think the winner for the best name of an exoplanet I've seen so far is this one, Coconuts 2b. I think they came up with the name and then reverse engineered it to mean cool companions on ultra-wide orbits. In other words, planets that are a long way from their parent stars. And they were particularly interested to see how large a solar system could possibly be. And this one, it's been calculated. Remember, 1 astronomical unit is the distance from the Earth to the Sun. This planet appears to be 7,500 astronomical units from its star, an awful long way from its host star. We take 1 year to go round the sun. This would take perhaps 1 million years to go round its star. A rather tricky thing to pin down, but kudos on the name, nothing else. At least they're starting to think about what they're going to call these things. But I think the prize for the weirdest exoplanet, well, one of the weirdest so far, especially as we approach Halloween now, is this one, which goes under, again, the unpronounceable LHS1140b. This is an eyeball planet, or at least it's thought to be. There's a certain amount of artistic license here, but it's based on what we understand about the properties of this planet. Its temperature, we believe, is such that it's probably an ice planet. Okay, fine. It's an ice planet, a bit like some of the moons of Jupiter, for instance. However, this is actually quite close to its host star. You can have an ice planet close to a star as long as the star isn't too bright. In other words, if the star is quite dim, then you can have an ice planet that's relatively close to the star. And it's close enough such that it'll be tidally locked. It's been calculated from the gravity that the star will tidally lock the planet. In other words, the planet will always face the star. It won't, like the Earth, turn in 24 hours and continually show a different face to the sun. So if this is an ice planet and one side of the planet is always facing the star, that side of the planet is going to get a little bit warmer than the night side of the planet. So maybe it's an ice planet in which one little patch immediately facing the sun has melted. So maybe it's an ice planet with an ocean. So it might look a little bit like that. Basically ice, but one patch has melted and produced an ocean. And the idea of having an eyeball planet like that, again, we can't be absolutely sure, but that's our best guess as to what this might look like based on the characteristics that we can measure. There are a number of missions, space telescopes, as well as projects on Earth, for finding and exploring and discovering new things about these exoplanets. These two are not designed to find exoplanets. Gaia, which was recently finishing its mission as of early 2025, it's finished its 10 years or so, 12 years perhaps, of mapping out stars in the Milky Way. And we all know about the James Webb Space Telescope launched Christmas Day 2021. Gaia's job is to map stars very accurately to precisions of a tiny, tiny fraction of an arc second, being 1/60th of an arc minute, being 1/60th of a degree. So absolutely tiny angles can be determined for stars in the sky, and if Gaia sees a star that appears to be wobbling, then again we can infer the existence of exoplanets. So Gaia is finding exoplanets by accident. Its job is to map where the stars are. By accident, it's also finding exoplanets. James Webb Space Telescope doesn't find exoplanets, but it might be told, go have a look at this one in more detail. Other telescopes have found these exoplanet systems. James Webb has the ability, with a large mirror and its sensitivity in the infrared, to go and see more detail, as we saw before, the disk of planetary formation around the star Fomalhaut, for instance. So neither are finding exoplanets, but lots of missions are dedicated to the idea of finding and studying exoplanets. Some of them are now finished, such as Kepler, which back in the noughties and teenies was finding a lot of exoplanets, and some, you can see from the dates, are going to be launched fairly soon. The European Space Agency is going to be launching the Plato system in another year or so, and if a certain individual doesn't cancel the NASA project slated for 2027, then the Nancy Grace Roman mission hopefully will again launch in a couple of years or so. Its future is now in doubt, shall we say. A long time into the future, you can see the date on this one. If these telescopes are successful, which I'm sure they will be, in finding lots of new exoplanets, there is definitely interest in having more detailed study of those worlds which we believe are habitable, rather than all of the planets in the exoplanet zoo. So there's this idea of a habitable worlds observatory, specifically for looking at Earth-type planets. But that won't be, as you can see, for quite a few years yet. But with the Nancy Grace Roman, I said earlier that one way of directly imaging exoplanets is, within the telescope itself, block out the starlight and then see what you can see of planets. That should work, but you are still letting very bright light from a star into the telescope, and it will inevitably scatter. You can't reduce, when you send light through optics, regardless of whether it's pieces of glass or mirrors, some light will be scattered. So if you've got a very bright star next to a very faint planet, it would be better not to let the light into the telescope in the first place. So rather than have an occulting disk, a tiny one inside your telescope, there's the idea of, why don't we have an occulting disk outside the telescope? So there's a thought. You have a star shade, a huge occulting disk, 100 meters in diameter, which unfurls like a petaled flower, and then is sent off a long way from the telescope. 50,000 kilometers away, the star shade would be flown to another position and placed precisely in front of a distant star. And when it does that, hopefully it'll then be possible to see any planets which are going round that very distant star. Yes, it'll take incredible choreography to get a spacecraft and a star shade in exactly the right place to block the light from a star to then see the planets. But it's thought that that would still be preferable to blocking out the light inside the telescope, even though that's easier to do, because you wouldn't be letting any of the starlight into the telescope itself. So that's still an idea rather than something that has yet been funded. I mentioned right at the start that we, in principle, can look for life on exoplanets. How do we go about doing that? Well, if we think about a planet that's transiting, we can think about it orbiting the star. Sometimes it transits in front of the star, and sometimes, of course, it goes behind the star, if we think about looking at it edge on. If we take all of the light from that system, star and planet, we don't have to be able to see the difference in the two, but if we take all of that light and look at it spectroscopically, then when that planet goes behind the star, we lose the light from the planet, and so the spectrum of the pair of them will change. And if we look for differences, we might be able to tell what the spectrum of the planet is. Also, when the planet comes in front of the star, if the planet has an atmosphere, some of that starlight will go through the atmosphere. And depending on the wavelength of the light you're looking at, some of that light might be absorbed by the atmosphere. You can choose to observe the star system at a wavelength that you know is absorbed by a particular molecule, whether it be CO2 or water or carbon monoxide or something else. And if you do that, then the apparent size of the planet will change. Because if you're looking at a planet with no atmosphere, it'll appear to be a certain diameter. But if you're looking at a wavelength that's going to get absorbed by the atmosphere, the planet will appear to be larger. It'll basically block more of the light from the star, because some of the light will be absorbed by the atmosphere. So what that means in practice is, if you look, again, this is actual data from the James Webb Space Telescope, if you look at the drop-in starlight and look in detail at how deep the dip is, you'll find that the red dots corresponding to one wavelength are a little different, not quite as deep, as the blue dots at a different wavelength, or the yellow dots at a different wavelength. If you choose the wavelength corresponding to particular molecules, you can figure out whether those molecules are present in the atmosphere of the planet you're dealing with. And James Webb has done this for a few candidates, not that many yet, but it has looked at the spectrum of the atmosphere of planets. And basically it then says, right, I'm fairly sure that in this particular planet's atmosphere there is sodium and water and carbon monoxide and carbon dioxide and sulfur dioxide and maybe other molecules as well. We have not yet found an atmosphere with a smoking gun that tells us, yes, that particular atmospheric composition could only have come about if life exists on that planet. But that is the hope, that one day, if we look at enough atmospheres, we will find some that tell us life has evolved on those planets. Not there yet, but watch this space. This is just a little graphic that gives us an idea of how things have changed. We're going to look at how planets have changed, exoplanets, numbers have changed from 1992 to 2024. Each dot here represents a planet. On the vertical scale is how massive the planet is, and the horizontal scale is how long does it take to go round its host star. Our own planets have been placed here, again, just for context, so you can see what's happening. If I run the graphic, as we're going through the 1990s, we can start to see that we're picking up various exoplanets, especially those of a mass similar to Jupiter. As we go into the noughties, the Kepler space probe is starting to pick up lots of new exoplanets using the transit method. And the colors simply refer to the method that provides us with that data. As we run forward to 2024, we see thousands upon thousands of exoplanets have now been found. And we also sort of notice they don't appear to be scattered uniformly, they appear to be clustered. There appears to be a large cluster just here next door to Jupiter. There appears to be a large cluster over here with the same mass as Jupiter, but a lot closer to their parent star. And there appear to be a lot smaller planets as well. But you might say, well, surely this tells us that not many of these exoplanet systems look like our solar system, because our solar system seems to be an outlier on the bottom right of this diagram. But we have to remember about observational bias. In other words, we're looking at stars which might have enough mass to make the star wobble, or are big enough to block some of the star light. That means it's always easier to find Jupiter-sized planets than it is to find Earth-sized planets. So we can't take the distribution of these planets as an indication of this is typical of all of the solar systems that are out there. We have to factor in the fact that some are easier to find than others. And generally speaking, exoplanet systems which have a really big planet close to the star produce a much bigger wobble, and that's easier to see than other exoplanet systems. So we just have to bear that in mind. When we found not a few thousand, but tens of thousands or hundreds of thousands of planetary systems, then we'll have a better idea of how many of them look like our own solar system. So if you want to learn more about exoplanets, NASA has a dashboard in which every exoplanet that has been found is documented, catalogued, and you can go and find its diameter, its mass, how far it is from its host planet, etc. And I've said that keep an eye on what's happening in the next few years, because the Europeans are going to be launching Plato in the next year or so. Maybe NASA is going to be launching the Nancy Grace Roman Space Telescope in the next couple of years, and there are, I'm sure, some very interesting results yet to come from exoplanet systems throughout our Milky Way. Thank you very much.